Welcome to our third lecture of our machine learning series, in which today we are going to discuss one of the most popular classification algorithm, that is logistic regression. So let's go to our writing screen to discuss more about it. So first, let's write our topic name, which is logistic regression. Regression. This is our topic. So this topic is very much similar from the topic that we have discussed earlier, that is machine learning. Oh, sorry, that is linear regression. Okay, so let's define a data set first before discussing the topic. Uh, for example, let's study our pass slash fail. Okay, 2 fail, 3 fail, 6 pass, 8 pass, 1 fail, 0 fail. Okay, so as you have seen that this is our toy data set or demo data set that we have created. So let's plot this data set on a graph. Okay. Here is the x and y axis, and let us denote, let's, we are, what we are going to do that the study hours that are fail, we are going to give it 0, and the study hours that are pass, we are going to give it 1. Okay, so let's denote it by red pen. So 0 is fail, 1 is also fail, 2 is also fail, 3 is also fail. Then let's uh, let's write the uh, here 0, 1, 2, 3, 4, 8, 5, 6, 7, 8. Okay, now let's denote the point. So the study hour 0 is fail, 1 is also fail, 2 is also fail, 3 is also fail. Then we have 6. 6 is pass. Okay, 7 is also pass. 8. Let add some more data points in this data set. So 4. Let's denote its pass. 5 pass. 6 we have done already. 7 pass. Yeah. Pretty clean data set. Okay. So 4 is our pass. 5 is our pass. 7 is our pass. Okay. So here, as you can see, we have drawn our data set. Or let me do one thing. Let us remove 7-1 and 8-1. You will understand why I'm removing these data points in the later part of this lecture only. Okay, so as you can see here, the data set that I have drawn on the graph, it is very difficult to find a best fit line here. For example, we can probably make this line the best fit line, or we can slightly move it up. Line should not have a curvature, sorry for that. Okay, so as you can see, it is very difficult to draw the best fit line because there is no best fit line that we can draw. So what we can do here, we have to squash the best fit line into these. We have to make this our line, our deciding points. Many of you can think here that we can make a halfway point in the y-axis, which we can plot as 0.5. So each point, okay, so each point, many of you can think like this, that each point that lie below this 0.5 x 0.5 point, for example 1 here, 2 here, 3 here, we can denote it as fail, and the points that are 0.5 or more than that, we can denote it pass. For example, this point, this point, this point. By following the same linear regression algorithm, many of you can think like this. But what if in this graph only we draw some outliers that we have drawn previously? For example, the data point 7, pass, 8, pass, Then what will happen to our best fit line? There will be another some more points, and our best fit line will have a different curvature. Can I rotate this? Do I have the power to rotate? I don't think so. So let's remove this line. Hmm. Okay. Now the line can be more tilted like this if we follow the earlier linear regression algorithm. And now you can see that the point number 4 lies below our 0.5 mark. But here in our data set, it is considered as fill, but the algorithm will consider it as false. So what we have to do, we have to change this line. We cannot draw the line based on the linear regression algorithm that we have discussed earlier. So let's first remove this graph, or let it be the graph. Let it be. Let's do not delete the graph. So let's draw another graph. What graph we are expecting in the logistic regression algorithm, which is uh, 0, 1, 2, 3, 4, 5, 6, 7, and here 8. Okay, like this. Let's denote the data points by the red ink, so it will be very convenient for you. 1, 2, 3, and 4 is our pass. So 4, 5, 6, 7, 8. So what we want here is this. Here, let's denote 0.5. Let's denote 1. We want to squash the linear regression best fit line into this format. So what we have to do? First, let's consider the hypothesis of our linear regression line. I don't know why I have deleted the line. Let it be. Okay. So in the earlier lecture, we have discussed that the hypothesis of the linear regression graph or the best fit line was h of theta of x was theta naught plus theta 1 x1. Okay. So what was to understand it to the layman terms, theta naught was our bias term and theta 1 was our slope of the x part. Okay. So theta naught was our bias term, theta 1 was our slope. So now let's see the hypothesis of our logistic regression graph. So we have not done anything of that much here. We have just applied an activation function which is called as sigmoid. So if we apply in this linear regression hypothesis, if we apply sigmoid activation function, activation function, let us denote that the sigmoid activation function as g of x. So g of x is our, for this particular algorithm or for this particular lecture, we are denoting g of x as sigmoid activation function. Let us write again because we can. Activation function. Okay. So what we can write here by transforming the above equation, h of theta of x is equal to g of z, where z belongs to theta naught plus theta 1 x1. Okay. So now you might be wondering what is sigmoid activation function. So what is sigmoid activation function is simply 1 upon 1 plus e raised to the power minus z. Okay. So if we expand this equation, the above equation, so we will get, let us erase this because we are writing the same thing. I don't know why I have erased. I shouldn't have erased, but I have erased. Okay. Jokes aside. 1 plus e raised to the power minus z. Now, let's put the value of z from here that we have assumed earlier. So, after more expanding this equation, h theta of x will be our 1 upon 1 plus e raised to the power theta naught plus theta 1 x1. Okay. This equation, this is our uh, hypothesis of logistic regression. If you want, you can reduce this part or change this part or substitute this part to theta transpose x. Okay. So if we substitute this part to theta transpose x, then our new and final hypothesis function of the logistic regression will be 1 upon 1 plus e raised to the power theta transpose x minus. I forgot minus here. So this is our final hypothesis function of the logistic regression. Okay. Now let's calculate the cost function. If you remember the cost function of linear regression that we have discussed in the earlier lecture, let's write it. Or first, cost function, cost function of linear regression, linear regression. So if you remember the cost of the linear regression function, it was j of theta 0, comma theta 1 upon 2m, summation of I is equal to 0, same theta h of theta of x I minus yi whole square. Now, you will be amused to know, or I will not tell you, I will show you. So you will be amused to see that the cost function of logistic regression, let me write it. Cost function of logistic regression. Okay, sorry for my handwriting. I don't know why I am so excited telling this. J of theta 0, comma theta 1 is equal to 1 upon 2m. I is equal to 0 to m. H of theta of x I minus yi whole square. See, here is the fun part. Both of the cost functions are same. Do you think so this? You are then wrong. Because, let me tell you, this is the most shocking part. Because here h of theta of x is theta naught plus theta 1 x. But here h of theta of x is 1 upon 1 plus e raised to the power theta transpose x. You can see we have derived it here. So here the cost function is this. Boom, boom. Sorry for that. Okay. Now this is the cost function. Let me remove this or let me be it here. It looks good. Okay. See, if you draw the cost function of linear regression, okay, here is a bit of problem here. Okay, let me tell you that also. So if you draw cost function of linear regression, it was like this. Okay, so it was like a parabola which has a global minima and no local minima. So there was no problem. These types of functions are called convex function. Okay, convex function. Okay, but here if you draw the cos function of, let me take the next page. Sorry for that. If you draw the cost function of logistic regression, let's draw it. Cost, yeah, draw. Let's write draw also. Draw the cost function. Yeah. Is it recording here? Huh? I was afraid a little bit. Cost function of logistic regression. So if you draw the cost function of logistic regression, it will be like this. Uh, don't know. My drawing is very poor. Let me draw it again. Have patience. It is similar like this, okay? It is not exactly like this, but actually similar like this. So these type of functions are called non-convex. Sorry on my spelling mistake. Let me erase it. Convex function. So this is a non-convex function. Why this is a problem to us? Because here you can see here are lot of local minima here. Local minima. Yeah. So if we run the gradient descent algorithm in this type of function or in this type of cost function that we have written here, it will stuck at the local minima. It can, let me change the ink for you. It can stuck here, it can stuck here, it can stuck here, it can stuck here. But we want that our cost function should come at here, which is the global minima, which is very difficult or not possible with gradient descent. Okay, so what we will do, we will transform our cost function. So our new cost function will be cost of. First, I will write the cost function, then I will describe you the cost function. Okay, the cost of h of theta of x I comma y is minus log of h theta of x when y is equal to 1 and minus log of 1 minus s theta of x when y is equal to 0. Okay, so this is our modified cost function. If we draw the graph of the our modified cost function, it will come like this only. If you don't believe me, you can go and draw the graph. I am not proving that. But if you want, you can draw the graph in the graph simulators or anywhere. You will get graph like this. So here, our main aim was to make the cost function a convex function that we have done. So if you want to write this equation in a form of equation, okay. So let's write this equation in the form of equations. Cost of h of theta of x comma y equals minus y log of h theta of x minus 1 of minus y log of 1 minus h theta of x. So if you look at detail in the cost function, both of these functions are absolutely, bear my spellings, are absolutely same. Because if you put y equal to 0, this function will get cancelled out because here is multiplication of y. If you put earlier I have put y equal to 1. Okay. If you put y equal to 1, this function will cancel out because 1 minus 1 is 0. So absolutely the same, sorry, the same cost function. So if you want to write the cost function again, okay, let's copy this function only. Okay, so it will be easier for you overall. Boom, copy, copy, copy. Okay, it has copied, paste. So here was our cost function. Now what we are going to do here, let's erase this. So let's remove this box and let's remove this function. Remove. Sorry for that song, or you can say jingle. Okay, so what we are going to do is take the minus common and put it. Okay, so why? Sorry for that joke. Y log of h of theta of x plus 1, sorry for that, 1 minus y log of 1 minus h of theta of x. So this is our modified cost function. And if you draw this cost function in a graph, it will be a convex function. And that was our main aim for all these calculations. I am also tired of these calculations. Okay. So now what we are going to do, the same thing that we have done in the linear regression after calculating the cost function, which was now, sorry for that, which was to, uh, actually my throat is paining a little bit, so that is why I have taken the pause. Okay, so what we are going to do is run a convergence algorithm. Run a, let me make it easier for you. Converge this cost function by gradient descent. So now what we are going to do is run the gradient descent algorithm on this cost function. Let me you must know the gradient descent algorithm as I have discussed in my previous lecture also. But if you don't know, there is no problem that I will write it. Sorry for that. So what we are going to simply do is converge j of theta naught comma theta 1. Let me write it here. New is equal to j of theta naught comma theta 1 old minus derivative of d of dx. Uh, Let me copy it. Copy, paste. So now we are going to uh, derive this cost function again and again and again. If you are not able to understand this part, you can watch my first lecture in which I have covered linear regression. There I have covered gradient descent in very much detail. This is gradient descent is that type of algorithm that you will use in almost every machine learning algorithm. In deep learning also you might use it, but in almost always machine learning algorithm you will use gradient descent. Okay. So you will convert this algorithm on global minima, on global minima. So this marks the end of our lecture. I hope to see you in the next lecture soon. Till then, keep studying. Bye, Bandhu.